I'm going to talk about modeling ice sheets. And this picture that you can see here is a picture of some ice in northern Greenland. And I think it beautifully illustrates the way that the ice flows, which is a lot of what I'm going to talk about. And it's a lot of why this has interested me. So the outline of my talk, I'm just going to give a bit of background and motivation for why I'm interested in this and why I think it's an interesting subject. I'm going to talk about a pretty simple model of an ice sheet, although you'll see that it sort of immediately gives rise to some complexities. And then, depending on how much time I have, I've decided to focus on two bits of work, or sort of broad bits of work that I'm interested in. One is focusing on what happens on the surface of the ice, and one is what happens on the base of the ice. So these are not going to be the basics, but they're just some interesting mathematical models. This equation is inspired by the government's level of equations in its dimensional inconsistency. But hopefully it makes the point that is the driving motivation for this, which is that the total amount of water on the Earth is basically constant. And most of it's in the ocean, but a large part of it is locked up in the two big ice sheets in Greenland and Antarctica. And so the size of the ice sheets is the dominant control on sea level. And if the ice sheets get smaller, then sea level goes up. So that provides the main motivation for a lot of my work. And the basic question that we're interested in is what controls the size of the ice sheets? Why are they the size that they are at the moment? And what controls how fast they will change size? This is just a picture of it's a sort of satellite image of the Antarctic ice sheet, which has got, as you can see there, 27 million cubic kilometers of ice. If you melted all that and spread it out over the whole of the ocean, that would be equivalent to almost 60 meters of rise in sea level. Currently, Antarctica is losing mass, so the ice is melting on average at about 100 gigatons per year. That's a large number, which is probably not very meaningful. That corresponds to about 0.3 millimeters per year of sea level rise. If you spread it out over the whole Earth, the way that sea level rise works is not quite like that, because the rise is unequal, because the continents themselves are moving up and down, partly in response to the melting of the ice. And just, I think this kind of useful just to have this in mind, that if you just simply work out how long, given the current rate at which ice has been lost from Antarctica, if you work out how long it would last, it wouldn't disappear for 300,000 years. So the timescales involved here are quite long. This is a Greenland ice sheet, which is the other big ice sheet on the Earth, although quite a bit smaller, about 10 times smaller. And it's got enough ice to raise sea level by 7 meters if it all melted. But it's melting faster, because that area of the Northern Hemisphere is one that's had the most significant global warming in recent years. So there's a lot more melting in Greenland. 200 gigatons per year, by the way, that's around about the total amount of rainfall that the UK gets. So all of the rain that falls in the UK all a year, that's about 200 gigatons. It's a bit more than that. If it kept melting at that rate, then it would all disappear in 10,000 years. So still, that's quite a long time. But part of the interest here is that we've seen recent observations have suggested that the rate at which both of these ice sheets are melting has increased. So there's an interesting question as to how much that will keep happening. If you look back in the past at how sea levels changed, in this diagram, sea level, the time goes from right to left, and what you're looking at here is the ice ages. And so this is sea level. The vertical axis is about 100 meters, and so as it's going up and down by quite a lot, this is the growth of big ice sheets like covering the UK and North America as the sea level is going down. and then when they melt, the sea level goes up again. So we're currently on the left-hand side of this diagram. And the rates at which sea level has risen in the past are up to several centimeters per year, compared to the 3 millimeters per year that we get at the moment. If we just zoom in on the last bit, this is where we have better records. So although this is still back, this is still measured in thousands of years, time now runs from left to right, just to keep you on your toes. And so this was the last deglaciation. This is when all the ice over the UK was melting. And so sea level was going up about 10 times the rate that it's currently going up, partly just because there was a lot more ice that could melt. It then stabilized, well, more or less stabilized for most of the last 10,000 years. And then the last bit here, so this is zooming in now on the last 300 years, where we do have much better records. It started to accelerate, going up again. The last 50 years or so, it's been going about 3 millimeters per year. And then the right-hand side of this plot are projections based on models that have got quite a large amount of spread as to how much this is going to go up in the future, but likely maybe up to a meter above. So 0 here is a little bit arbitrary. 0 is where it was in 1700. It might be about a meter higher than that by the end of the century. And so that would cause quite a large change in like the number of, well, it would displace some people from their homes, but it would also make things like storm surges much more common. So it's not necessarily just that the base level goes up; it's the fact that you get much more flooding if sea level is that much higher. So that's the motivation. Let me just talk a little bit about how the ice sheets work. Hopefully this is not too noddy. They grow because of the snow. It snows in the winter, and then in the summer it melts. And so you go through a cycle of snowing and melting, and snowing and melting. It looks like this. You can see those flicking back and forth. And what I've drawn here is a horizontal dashed line, which is where above that, there's more snowfall in the winter than there is melting in the summer. So you have a net accumulation of snow above that line, whereas below that line, you have net loss of ice. And so the accumulation of snow in the middle then causes the ice to spread out under its weight. This line is called the equilibrium line, or equilibrium line altitude, usually called ELA. So this is quite important, and it's going to be important in the model that I show you. So anywhere above this, I have accumulation on the surface. Anywhere below it, I am taking away ice, which I've drawn that as just running off. I'm going to call it runoff, and I assume it just disappears somehow. And so the ice is flowing in order to make this work. So it's got to spread out, and that happens under its weight. And I'll talk a little bit about this in a second. And I've just introduced a few things that are going to be part of the notation that I use here. So the ice thickness is h, and the velocity is going to be u. And I'm going to be interested in the velocity profile. We have accumulation, that's snowfall, the A, and we have runoff, which is the R. And also, I've drawn it going into the ocean here. It breaks off icebergs when they go into the ocean, and that's what I'm going to call QC, which will come in later on. And the basic model that we use to describe these is a kind of depth integrated mass conservation equation, which I hope will be familiar, at least in the basic idea to most of you. So it's going to be an equation that looks like this. The ice sheet extent is much bigger than it is thick. So like Antarctica is thousands of kilometers across, and it's a couple of thousand meters deep. So the aspect ratio is about 1 in 1,000. These are pretty thin, well, yeah, they're relatively thin layers, but they're obviously huge scale. So this is, I don't know how well this movie is going to come across. I think it probably doesn't come across very well on Zoom. This is a time-lapse movie, and you might get even more flickery than the actual thing is, trying to show the movement of a big glacier that's in Alaska. So this is not in Greenland or Antarctica, but it behaves very similarly. And what you might be able to see, I don't know whether you can, is the ice kind of flowing towards you, and then it breaks off into the ocean at a line which is more or less constant in position, which is called a calving front. And it's breaking off little icebergs that then flow out into the ocean and then melt. And this is partly what we've got to try and model. And the interesting question here is, why is the edge of the ice where it is? Right, there's obviously a kind of balance between the amount of flow coming towards that edge and the amount which is breaking off as icebergs. But what's determining where it is? That's part of the interesting modeling that we have to do. This is another movie which, again, might not come across very well, but you might see some stills. This is a compilation from a satellite image of the surface velocity of the ice sheet. So this is now the way that we work out how fast the ice is moving, by taking satellite pictures of the same place at 2 times, and then identifying features in the images which have moved. And then that tells you, if you can work out how far they've moved, that tells you how fast the ice is moving. And then this has been turned into this exciting looking animation, where it looks like the ice is moving at the speed of light. The ice is moving obviously quite slowly, and during the time over which these measurements were taken, which is while there's been satellites looking at the ice sheet, which is about the last 20 years or so, most of the ice has not moved even the length of one of those little arrows. But they've animated it to make it look like it's more exciting. The colors are showing the magnitude of the speed, and you can see that the ice is being funneled into these fjords, which are then where it's coming out and breaking off as those icebergs that you saw in the previous movie. So that's the way that we detect how fast the ice is moving nowadays. This first started happening in the 19th century, and it was actually mostly Victorian gentlemen who were enjoying going to the Alps in the summer to do mountaineering, which was sort of taking off those times. And they obviously saw lots of glaciers, and they got interested and started having quite a lot of arguments about how the glaciers were working. It was obvious that the ice was moving. So this is a sketch on the right that you see of the Mer de Glace, which is coming down from Mont Blanc. Some of you may have been there. And it's got these really nice patterns of dirt on the top of it, which they observed, and which could really make it look like it's flowing. And they could tell that it was flowing, obviously, because you can see it having moved when it's moving quite fast. But they started to notice things like the fact that the ice in the middle of the glacier was moving much faster than the ice at the edge, and they thought, well, this looks a bit like a viscous fluid, but they were kind of struggling with the idea that what seems to be a solid material is behaving like a fluid. And this was a time when there were sort of religious feelings that this was making everything feel a bit shaky if what was supposed to be a solid was flowing. But gradually this came to be accepted that that's what the ice does, although they didn't really understand why in those days. But that has, I guess, thinking has evolved to the point that we now just accept that we're going to treat the ice as a viscous fluid, and that's what I'm going to do. And so this is now quite standard, that if we're interested in the behavior of glacial ice on timescales that are longer than a day or so, then we're going to treat it as a fluid. But the experimental measurements suggest that it's not a Newtonian fluid. It has a non-constant viscosity. So this is a relationship between the strain rate, epsilon dot, and the stress, tau, where in the exponent n, the experiment suggests is about 3. That means it's shear thinning. So the faster it's moving, the lower its viscosity. when we do modeling, or at least when I do modeling of this, I tend to write it in the form of a Newtonian fluid, which is what you see here, but with what's usually called an effective viscosity. So the viscosity is not a constant, it depends upon the stress. That tau is the second invariant of the stress tensor tau ij. This is a model that's also used for various other sorts of fluids, particularly polymer fluids, which exhibit similar kinds of behavior. Confusingly, in a lot of the literature on non-Newtonian fluids, n is usually taken to be 1 over n here. But in all of the literature studying how ice flows, it's always taken this way around. And the A is the sort of coefficient, which is like the viscosity. That depends on temperature quite strongly, which also makes this more interesting. So that's what we're going to do. And so what you see on the right here is just some data from experiments. We're looking at stress and strain rate, which have been used to fit this experiment 3. The actual structure of the ice, I don't know if anyone's interested in this, but so it's really a polycrystalline material. That means it's made up of lots of individual ice crystals, but they're all sort of squished together. They've all got different orientations. Usually it's easy to deform an ice crystal in one particular direction because of the crystal structure. But the glacial ice is made up of a whole load of crystals which have all got different orientations, and therefore it doesn't really have a preferred direction that makes it easy to deform in. But the macroscopic behavior of the ice, which I've written as viscous because it disappears as viscous, occurs through mainly through dislocation creep within these crystals, but also a bit of sliding on the boundaries between the different grains, which you can think of as just different crystals. Okay, so this is what we're going to take for the rheology of the fluid. Although sometimes when I'm modeling this, I sometimes just make it Newtonian just because it makes things easier. This is the pictures that I usually show to try and convince people that ice is like a fluid. This is a glacier called the Elephant Foot Glacier, which is, I think it's on Axel Heiberg Island, which is in the Canadian archipelago, north of Greenland. But you can see that the ice is spreading out under its weight. The Reynolds number, when you have a non-Newtonian fluid, it's a bit ambiguous what the Reynolds number means because of the fact that the viscosity is not constant. But basically, however you work it out, so you can work out an effective viscosity for a given stress rate, and you can work out the magnitude of the stress that's based on the weight of the ice. However you work it out, it comes out to be very small. So these are low Reynolds number flows. The inertia is obviously not important. When I say small, I mean 10 to the minus 10 or something. So we're going to do Stokes flow, but with a non-constant viscosity most of the time, which makes Stokes flow would normally be linear if you were doing Newtonian fluid, but in this case, it's going to be non-linear. So that brings me on to this slide, which describes a very simple model for an ice sheet. And we saw this cartoon picture at the top earlier on. So the basics of the equation is a mass conservation equation. Q is the ice flux. That's the integral of the horizontal velocity from over the depth of the ice. I'm calling the bottom of the ice B and the surface of the ice S. And the difference between those is h, the thickness, and that's the thing that we're mainly trying to work out how it evolves. And the simplest model for this is that we use lubrication theory. So we throw out lots of terms from the momentum equations based upon the aspect ratio being small. A lot of this works quite similarly for a power law fluid than it does for a Newtonian fluid. Lots of you will have done this for a Newtonian fluid, maybe few of you have done it for other sorts of fluids. But because the main point behind lubrication theory is that you have one of the stress components dominating all the others, the vertical shear stress. And when that's the case, it makes some of the complications of having a non-Newtonian fluid not be quite so complicated. And that means that you can still make some progress. So this expression that you see here for Q has come from doing lubrication theory. And I'm assuming that the A is a constant. So I'm not worrying about the fact that there might be a temperature difference between different bits of the ice. So the A was the thing that's like the viscosity. And then you have this H to the N plus 2. So there's some power of the ice thickness, and then you have some power of the slope, the surface. S was the surface. So this basically says that the ice moves down its surface slope, and it moves faster when it's thicker. If you're familiar with lubrication theory for a Newtonian fluid, this would be h cubed over 3 times ds dx, and then this would all be 1 over the viscosity. And so this basically comes out in just the same way. And then I've added on this thing called UB, which is the sliding speed. And that's because the bottom of the ice is often melting. There's a layer of water that allows it to slide over the rock. And this is quite important. I'm going to come back to this later on, but for the moment, I'm just going to forget about it. In order to calculate that, we need a slip law, which relates the stress that the ice is exerting on the rock underneath to the sliding speed. And so that the coefficient C there is sometimes called a slipperiness. It could be related to the inverse of a slip length, if you know about, if you think in terms of slip lengths. But this basically parameterizes something which is going on a much smaller scale. And if I have time at the end of the talk, I'll talk a bit about that. For the moment, I'm just going to ignore sliding and assume that there's no slip. So this is just a normal spreading film of fluid, albeit non-Newtonian. And so the source terms in this mass conservation equation, remember, are the snowfall and the melting and the runoff from the surface. So I think it's kind of interesting just to think about almost like a toy problem. If you think about putting the ice sheet on horizontal topography, so that means it's a completely flat continent, then this equation can all be, and if we're assuming no slip at the base, then the equation just becomes this thing, which is a nonlinear diffusion equation. And I've assumed here that the source term, I want to put those on, the source term, which is the A minus R, I'm assuming that it can be written like this. So this is trying to encode this equilibrium line, which I've written at the height SE. So I'm assuming that this depends linearly on the ice thickness, such that if the ice thickness is above this line, then this is positive. And if it's below, then it's negative. That's the simplest way that we can do that. And actually turns out to be a pretty good, a good approximation. SE is something that basically depends on air temperature. And that's something that we can use in this model as a way to explore how the ice sheet responds to changing climate. As the climate gets warmer, SE increases because you have to be at higher elevation to have less melting. That's all mainly just due to the fact that the air temperature gets colder as you go up in the atmosphere. So anyway, the structure of this equation is then, having written the source term like that, actually becomes a kind of reaction diffusion equation. And it's similar to the equation that you get in studies of like combustion and things, because it can exhibit blow up, because your source term depends on H, right? You've got dH/dt is proportional to H. And that's part of what makes it a little bit interesting. but the non-linearity means that the solutions have compact support. This is pretty standard for these sorts of equations. I'm going to look for solutions which are of the form that's shown on the right here. So I'm going to make them symmetric, which means that they have to have a flat surface in the middle. And I'm going to assume that at the edge, which actually is a free boundary, we need to find where the edge is. I'm calling that xm. We assume that the ice has zero thickness, and then if you analyze, you make sure that you conserve mass basically at the front, then you can derive this kinematic condition for how that front should move. This is just a second order diffusion equation. So this is not, those of you who do like thin films and have to worry about the motion of the front in such problems, you don't have to worry about that here. Lubrication theory seems to work. Although you have to be a bit careful about the fact that in this case, dh dx will often be infinite at the edge. So h is going to 0 and dh dx is going to infinity. So you have to be a bit careful about evaluating the speed of motion at the front. And it turns out to be a bit different if the front is advancing or if it's retreating. So if it's retreating, then you have a finite slope at the edge. And if it's advancing, you have an infinite slope at the edge, but a finite fluid speed, which is the Q over H. So this problem has a steady solution for a given SE. And that's shown here. So the dashed line shows the height SE, and then the black line shows H. And you've had to find where the edge is to make this work. And so you have to make sure that the total amount of snowfall on the bit that's above the dashed line equals the amount of melting in the bit that's below the dashed line. But it turns out this solution is unstable. And that's basically because of this fact that you have dHdt is proportional to H. If you make the ice slightly thicker, then you'll have more of the region above the dashed line, and you won't have increased the region below the dashed line as much. And that means that you are going to have the ice sheet continuing to grow. If you shrink it a bit, it'll shrink. So this plot down here shows solutions over time, so that the different blue lines are different snapshots of the solution at different times, having perturbed it from that steady state. And either it shrinks until there's nothing left, or it just keeps growing and growing and growing. This is quite an important point about how ice sheets work, which is that if you make them big enough, then they'll just keep growing. And this is something that's been called the accumulation elevation feedback. Once they're tall enough that they poke their head up high in the sky, then it's so cold that they won't melt up there, and then they'll just keep growing. And this basically explains why the ice sheet takes up the whole of the island of Greenland and the whole of the island of Antarctica, which we don't usually think of as an island. But the ice sheet will basically grow and take up the whole of the continent that it's sitting on. And it then flows into the ocean, and that's what stops it from growing in the end. So we can make this slightly more complicated if we assume that there's topography which is not completely flat, so the bed's not horizontal, and then this equation is not quite so clean. And the other thing that can happen is that it now flows into the ocean. That means it doesn't go to having zero thickness at the edge. It goes to, the edge is now the position where icebergs are going to break off at this rate QC. And this is actually, we still don't know really what's the right way to model this. But it seems to be that a pretty good approximation to what happens is that the ice gets to the point where it's just about to float. So in B here is the height of the bed relative to sea level, which is Z is 0. And so this if H takes this value here, that means that the ice is basically floating at the edge. rho O is the density of the ocean, rho I is the density of the ice. And then this is like a kinematic condition, which says that if the icebergs are breaking off at a rate QC, then we'll arrive at this expression for how fast the edge of the ice moves. The calving rate, QC, the rate at which the icebergs break off, this is where it gets a bit more debatable. And this is a theory which I've been working on for a while, which I decided not to tell you about, but that says that the calving rate basically depends on the depth of the water. The thicker, the deeper the water is, the faster the icebergs will break off. This is complicated because the process of breaking off icebergs is something that depends on fracturing the ice, not something that's really described by this kind of viscous model. And it's not clear what sets the rate at which that happens. And this is actually one of the biggest uncertainties at the moment in understanding how Greenland and Antarctica are behaving, is that they seem to have started breaking off icebergs faster, but it's not totally clear why, and we don't really have a good model that can make predictions of that. Anyway, this is an option which we'll explore. If you do that, then you find that you can find stable steady solutions now when it ends in the ocean. And depending on the shape of the bed topography, which I'm assuming is fixed, then there might be multiple ones. So what you see in this picture is 4 different steady solutions, 2 of which are stable and 2 of which are unstable for the ice thickness, which have got different positions. They've got very different sizes of ice sheets, but they're all for the same height of this equilibrium line. So basically, they're the same climate. So this is quite an important point because it says that the size of the ice sheet is not just determined by how hot the climate is. It might be determined by the history in terms of which state it's in. And so from this kind of model, you can produce a bifurcation diagram. So what you see here is the height of the dashed line along the x-axis, and then the position of the edge of the ice sheet on the y-axis. And the dots are showing the solutions that you see on the left. And so if you now increase the height of this equilibrium line, so that means you're making it warmer, then the state with that's the furthest out, the largest ice sheet, will cease to exist after a while. That steady solution doesn't exist anymore, and then you'll have to go back to this much retreated one to have a steady state. And the rate at which that happens is controlled by this calving rate, because that basically controls how fast that position of the edge can move backwards. This suggests that an ice sheet like Greenland, probably every different outlet glacier has got a different shape of fjord. So what you're looking at here is actually probably just a model of one of those glaciers. And so as the climate changes, they're all going to go through these kind of bifurcations at different times. And that's kind of what we're seeing at the moment. The climate's getting warmer. So they're all generally retreating, but some of them retreat much faster than other ones. And that's probably because they've lost stability and they're looking for another place where they could be stable. This kind of behavior is often called, by the climate people, it's often called a tipping point, but this means a bifurcation point. People get very excited about this because it's thought of as an irreversible change, such that if we cooled the climate back down again, the ice sheet would not then grow, which is true. I want to say a little bit about more sophisticated models. Most of our models that we're dealing with now actually assume that the ice is actually dominated by sliding. So that this velocity profile that you see on the right-hand side, where most of the deformation actually occurs at the bottom, is more the picture that we have in mind. So that this is because the bits of the ice sheet that are the most interesting are the ones that are moving really fast. And so we actually don't care so much about the sort of internal deformation, which was what was included in that previous model. But most of the models that we're dealing with are these sort of depth integrated models. And we're also solving a depth integrated force balance equation, which then sometimes includes this membrane stress term. And some of you may be familiar with these sorts of models. But the basic balance here is between gravity, trying to make the ice spread out, driven by its surface slope and its thickness, and that balances this term CUB, which is the basal shear stress. And so this C, as I said, there's quite a lot of uncertainty about what that is. That's basically representing the slip at the base. If we want to do this properly, we have to couple this to a model for the ice temperature, although this is not always done, because the viscosity, which appears in this stress tensor, depends on the temperature. And it turns out if you look at the size of all the terms in the energy equation, everything's important, basically, except horizontal conduction. So you need advection, conduction, and viscous heating, which is not always important, but in this case is, which is the final term there, are all important. And there's also geothermal heating, which is the heat that's coming from inside the Earth. And that's quite important because the ice is so thick that it really insulates itself. And so this is just a calculation that came from a paper where we were interested in the internal melting of the ice, which happens because the lower layers of the ice are actually really warm. So this geothermal heats them up so that they're at the melting point at the bottom. That's why there's water underneath the ice, and that's what helps it slide. But also, if it's viscously deforming, then there's heat being generated inside the ice. And if it reaches the melting temperature, it must then start to melt. It can't go above the melting temperature. So there are various regions at the bottom of the ice that are actually melting, and they become like a porous mixture of ice and water. But I'm not going to say anything more about that. What I want to move on to talk about is the surface boundary condition that we have to apply to this, because there's some interesting modeling involved in that. And I realize that I'm probably going to run out of time. So I want to know what boundary conditions I should apply, both at the surface, so there's M minus R. I want to know what the runoff is, which is not totally obvious. And I want to know what temperature I should apply at the surface of the ice. The naive thing to do is to assume that that would be the air temperature. But as I'll show you, that's not quite what you need to do. So I'm going to talk about that. Some of you might have decided that you're not interested in ice. So I have a very slight diversion so that you can have something else to think about to work out how large Antarctica is. So here's an interesting question, which has been going through lots of our minds as we try to work out how many people we can invite round into our gardens at the moment. How many people could have a socially distanced picnic on the Antarctic ice sheet? Don't worry about the fact that it's too cold. So in the UK, at least, we need to be 2 meters apart. So we assume that that's the case. Although in America, it would be 6 feet. And I was quite amused by a friend of mine in San Francisco sent me this picture. There are no prizes for telling me what's geometrically wrong with that diagram. But if you're not interested in the rest of what I say, you can work out how many people we could fit in Antarctica. So now I'm going to tell you about the surface boundary layer. So on the top of the ice here, we got this layer of snow. Once the snow's been there for a year, it's called firn, but it's still basically just snow. And that's the porous material. And the question that I'm interested in here is what's the effective surface boundary condition that the ice sheet underneath feels as a response to what's going on within this layer of snow. Because there's accumulation of snow at the top. It forms snow that then compacts under its weight and eventually turns into ice. So this top layer of the ice is actually not incompressible, although in our models we usually just assume that it's incompressible and don't worry about this. But for this little part of the talk, I am going to worry about that. We want to know how much the snow melts when it gets warm, and so that involves doing an energy balance at this surface. And so this can end up looking quite complicated, but I'll just try to get the simple version of it. So there's a whole load of energy fluxes which have got to balance on the surface. There's like different radiation terms, and there's the one that dominates actually is a turbulent heat transfer from the air. So I'm going to lump all of this together and say that this can more or less be expressed as a kind of Newtonian cooling term with a heat transfer coefficient. Tf you should think of as the air temperature minus the ice temperature, and that balances conduction into the ice. And then this final term, which is the melting term. So this term is, L is the latent heat. So this term is 0 if there's no melting. That happens whenever the temperature is less than the melting temperature. And if the temperature reaches the melting temperature, then this term has to be whatever it needs to be in order to make this energy balance work. This is basically like a Stefan condition, conserving energy fluxes. But you had this sort of either-or statement, or a kind of complementarity condition, which you had to kind of solve as part of the problem to work out whether we're at the melting temperature or not. And in that case, is melting allowed or not? But this Tf is think of it as the air temperature that goes up and down, which is cold in the winter and warm in the summer, and that drives melting. The melt water that's produced there, this is why it gets interesting. What happens to that melt water? Well, some of it just infiltrates into the snow, and it can then refreeze, and some of it runs off, and then it eventually gets into the ocean. So the melt that's produced is got to be partitioned somehow between bits that go in and bits that run off. And so what ends up coming out of the bottom of this column, which is what ends up going into the ice sheet, is the net accumulation rate. So that's the accumulation minus the runoff. And well, then this is part of the question: what's the temperature of that stuff that's going down into the ice? Right, so this A minus R was the source term that we put in the mass conservation equation before. So I'm going to try and write down a model for what's going on within this little snow column in this region to try and work out what the temperature should be that I need to apply to the rest of the ice sheet underneath. The way this works is actually going to be quite different in the other regions of the ice sheet where the streamlines are emerging. Right? So this is where A minus R is negative. Now there you have ice effectively coming up out of the ice sheet. You might have a bit of snow fall in the winter, but the way that this works is going to be a bit different. Okay, so this equation, this slide is a bit heavy with equations. This is a model in which we have three variables, basically. The temperature of the snow, the porosity of the snow, and the saturation. So the saturation is the amount of the pore space, or the fraction of the pore space which is filled with water. So we're treating the snow as a mixture of ice, air, and water. For the air, we don't really need to model because it's so much less viscous and less dense than everything else. So we just ignore it. And so this is a kind of interesting, so there's quite a lot of complications that are going on, but the basic structure of the equations is that we just write down conservation of ice and of water, in which there's some source terms which reflect the fact that the water can freeze and turn into ice. And then we had to write down Darcy's law for the flow of the water, which is driven by gravity and by capillary pressure gradients. We have to distinguish regions where it's saturated and where it's partially saturated. So actually this water pressure here is the capillary pressure where it's unsaturated or where it's partially saturated. And it's something that we have to solve for where it's saturated. And the way that happens, it's a little bit complicated, so I won't try to explain that, but if you want to know more about it, I'll tell you about it. We couple all this to an equation which is describing the compaction. So the porosity is not fixed, but it's evolving. And it's evolving due to the fact that there's some phase change. So the porosity goes down when the water that's in the pores freezes. So this M is, for historical reasons, the melt rate, although it's always negative in this case, so it's always refreezing. But it's also mechanically compacting. So this is the settling of snow under its weight. There's lots of interesting questions about how you should model that. And what we chose to do in this study was to take an empirical relationship that people had come up with by measuring how fast this happens. So that's that curly C. And then we had to write down an energy equation because we need to know the temperatures in order to work out how much of this water is going to refreeze. And the interesting complications that come in this kind of model is that you then end up with interfaces between regions where there's water, regions where there's no water, regions that are saturated and regions that are partially saturated. And you need to make sure that you conserve everything at those interfaces, which is not a totally trivial thing to do, but quite fun. So this is just an example of the solutions of the model that we came up with, where I take some snow. This is the porosity of the snow. So it's largest at the top, and then it goes down to basically 0 at the bottom. And this is what snow typically looks like. And it's all cold, so minus 15 or so. And then I'm just going to melt the top surface of it. And the water that's produced is going to go down into the snow. So this is a movie where you just see some time steps. So the blue line here shows the amount of water filling up the pore space, which is effectively the region to the left of that line. And it's propagating down. The water's got to be at the melting temperature. So now that region of the snow has been warmed up to the melting temperature. But the way that happened was that the water that was going into the snow had to transfer some of its latent heat to the snow. And it did that by freezing. So you can see that when the water's gone in, it's actually caused a reduction in the porosity. So you get this quite strange front. This is like a wetting front, like water going into soil when you water your plants. But as the water goes in, it's freezing and making the pore space smaller. And the rate that it freezes at is controlled by how cold the ice is ahead of it. And so it keeps propagating like this. Then it becomes saturated at this point. Once it becomes saturated, then the snow starts to fill up. All of the snow, all the way up to the surface, is now full of water. At this point, everything that melts is now going to run off. So this is now the situation where the water is just going to go into the ocean eventually. And then it keeps going, and then you can actually get it forming a blockage. And then, so if you look at that through time, so this is time running along the x-axis. There's quite a lot to see here, but this plot here in the middle is showing you the temperature and the water content. So wherever it's blue, it's got water, and wherever it's red and yellow, it's the temperature. The way that we actually solved this, I didn't say, but the way we solved this was with what's called an enthalpy method, which is often a way that you can combine solving for the temperature and water content in these problems where you get the temperature kind of going between being below the melting temperature and being at the melting temperature. But this is a pretty non-standard one in this case. But you could do some interesting asymptotic approximations of this model to work out like what's the speed at which this front goes in. which is not just controlled by the amount of water that's infiltrating, but it's also controlled by the temperature of the snow underneath because of this refreezing effect that's going on at the front. And you can see that as you go across that front, the porosity has a jump because of the refreezing that happened. Anyway, the point of doing this was that we can then run calculations of what happens to this snowpack as you go through the course of a year. And so this is showing the same kind of thing. The important thing to take from this is that the top panel here shows you the varying effective temperature. That's the thing you should think of as the air temperature. So that's oscillating, and that feeds into this boundary condition. And then that drives this temperature profile that you see in the middle. And you can see these sort of seasonal waves of temperature, which hopefully is familiar to many of you if you've had to teach first year PDEs. You will know about these. But except that what happens in this case is that in the summer, just in the very peak of the summer, the surface starts to melt. So the temperature of the surface reached the melting temperature, and at that point we started producing water instead. And the water infiltrates into the snow, but it then refreezes again in the winter. So what I'm now going to do is just increase, so this is a sinusoidal variation of the temperature, oscillating around a mean, which is really quite cold. So this gives rise to a place where the net accumulation is more than the net melting. So if at this bottom plot here, you can see the pink lines are supposed to be the streamlines of the snow, which are basically going downwards, which shows that this is that region above the equilibrium line. If we make the temperature warmer, then we'll get more melting. And if we make it warm enough, then we will be simulating the region below that line, where there's more melting than there is accumulation. So this is what happens if we just increase the mean of that forcing temperature a little bit, so it's slightly warmer. We get a bit more melting in the winter. And now the water that goes in actually goes in much further, and in fact it then stays there all year round. So that the bottom of the snow now has water in it all the time. That's interesting because that means that the temperature that we should feed, this is all actually compacting. In fact, the bottom of the domain's off the bottom of this picture. This is turning into ice, but it's turning into ice that's at the melting temperature. And that's interesting because this is the case where the air temperatures, on average, is much below the melting temperature. But the temperature that we should be feeding the ice into the ice sheet model is at the melting temperature. And the reason is because all this melt that's infiltrated into the snow has taken latent heat with it, which has then warmed up the bottom of the snow. If I make it warmer still, in fact, let me make it very warm, then I get much more melting. In that case, we find that we now have these pink lines which are coming upwards. That's the ice is coming up out of the ice sheet, and the black color down here shows that this is really dense. This is ice, and we just have a snow layer building up in the winter, and then we just melt all of the snow in the summer, and all the water that's produced is then running off. So if you put all of that together, and this is how we're going to end this, then you find this plot down at the bottom right is the important one. As you increase the air temperature on average, then the temperature of the bottom of the snowpack is the blue line. So when there's no melting at all, they're the same. The snow is just the average air temperature. And when there is very little, when you have very warm temperatures, all of the meltwater that's produced just runs off the ice. In that case, you also have quite cold temperatures of the ice. But in this intermediate state, where the water is going into the snow and then refreezing, then the temperature at the bottom of the snow is actually at the melting temperature. So that's a kind of interesting feature of the way that the snow works. I don't want to bore everyone to death, so I'm not going to tell you about the next bit. But the water that does run off forms these blue lakes. If you've ever flown to America during the summer, you may, if you got lucky and didn't have clouds when you were flying over Greenland, and you might have seen some of these. Eventually, that water flows into these holes called moulins, and we think it then goes down to the bottom of the ice, although we don't know. These are kind of enormous big caverns with these waterfalls flowing into them. But that has a big effect on the way that the ice is moving. The red line here shows the ice speed measured by a GPS that's been stuck onto the ice surface. Basically, when you get all of this water flowing into those holes, the ice suddenly moves at twice the speed that it was previously moving at. This is something that Michael McPhail, who's currently doing a postdoc with me, is working on trying to model. And there's various theories about how that works, but in the interest of time, I'm going to skip this out. And if you want to know about this, then you can come to the virtual pub, and I'll tell you about that. This is just a picture of how mucky it looks underneath the glacier when it gets wet. And just before I finish, I will give you the answer to this question. At least I think it is. So I think that the right way to make as many people fit in as possible is to put us on a hexagonal lattice, although someone can correct me if I'm wrong. And so I think that we all need 3.46 meters squared for each person. And that means, given how large Antarctica is, that we could fit around 500 times the population of the world into Antarctica. But it would be quite cold. So I'll end it there. There's my take-home messages.